Okay, so last time we learned how to break two vectors, vector A and vector B, down into their vector components. And that's very important because now we're going to try to actually combine these two vectors, vector A plus vector B. To do that, you need to understand how they actually appear. You need to understand that vector A is actually made of vector AX plus AY. Vector B is made of BX plus BY. And we know that these have actual values. Let's see if I can bring this in. There we go. That end up looking like this. And so we have A of X was equal to 8.7 meters per second. A of Y was equal to 5 meters per second. Vector B, its X was 14.1. I left off the 0.1 meters per second, and a negative 5.1 meters per second. And this should make sense if we know anything about quadrants as well, because if you remember quadrants, then you should remember that in graphs you have 4 quadrants, 1, 2, 3, and 4, and X and Y are both positive in the first one. X is negative and Y is positive in quadrant 2. X and Y are both negative in quadrant 3. And in quadrant 4, X is positive, but Y is negative. And that's exactly what we found out. The components for A were both positive, X and Y. For B, that we can see is in quadrant 4, X was positive, Y was negative. And now that we have their values set up, we can go ahead and show you how to do vector addition. With vector addition, you need to understand you're going to be moving downward because you can only combine like components. And what we're looking to get is a resultant vector, which is going to have its own X and its own Y components. So resultant of X and resultant of Y. And we do that by adding straight down on our X and Y portions, okay? That means that if I add these together in the X, I'm going to get an R of X of 22.8 meters per second. And I'm adding to that the Y components, which actually, if you notice, because of the negative, are going to give us a negative 0.1 meters per second. So now we have our X and Y of our resultant vector, which means we can go ahead and start to solve for that resultant vector. So really, we can now set all of this up since we know that R has an X and a Y component. We can even draw it out to visualize it, the idea that it's going to have a X and a Y component. I will note that, again, you start putting components tip to tail. So that means you put X out there and its tip hits the tail of R. And then basically you're just combining from your point of origin all the way down to your finish line with your resultant vector. And you can see the direction that it'll be heading. Now, yes, I haven't done these to scale. I've exaggerated a little bit, of course. But you can also see that leaves us two things to get. We need to get the magnitude of the resultant, which is now our hypotenuse of our right triangle. And we need to figure out the angle. Well, I think that the magnitude is a lot easier because almost everybody remembers a squared plus b squared equals c squared. Or if you want to solve it for c, which we're doing, it's going to be c is equal to the square root of a squared plus b squared, right? In this case, c is actually going to be our resultant magnitude. And we can plug that in and get it pretty easy. So let's go ahead and do 22.8 squared. Oh, don't forget our units. So meters per second squared plus 0.1 meters per second. And yes, you can make it a negative, it doesn't matter. As soon as you square it, that negative goes away. And do the square root of it, and it's going to give us our actual resultant value, which, due to a rounding issue, still comes out to 22.8 meters per second, which makes a little bit of sense if you realize how incredibly small -0.1 meters per second is, and hopefully, when we calculate our angle, we'll find out it's almost perfectly straight. So how do we figure out the angle? Let's take a look. To calculate the angle, we need to use a trick with trig again. So we know that tangent of theta is equal to opposite over adjacent. Well, we have both of those, and we already figured them out before we recalculated r, and since r looks funny, we don't want to use that. So what we're going to do is we're going to take the inverse of the tangent, which moves that theta by itself, and it makes it inverse of tangent of opposite over adjacent. And we have all of these values. So now we can say that theta is equal to the inverse of tangent over our opposite, which is -0.1 meters per second, divided by 22.8 meters per second. And actually I can drop the meters per second because it's meters per second divided by meters per second, which means they're worthless. When I do that and I put it in my calculator, you're going to get an angle of 0.3 degrees, which is awesome because if that equals 0.3 degrees, then we can see that it's almost entirely in the x-axis, and that's why that value that we got there should be very close to that. And we now have our resultant vector. And so if I put these two together, I get a brand new vector. I get my resultant vector, which is equal to 22.8 meters per second, and is only 0.3 degrees below the x-axis. Why below, do you say? Well, remember when we put those together, we ended up still having a magnitude that pointed down of this r vector. So we know that it is actually in the fourth quadrant. So because of the r of y was a negative value, we know that it is below the x-axis. And that's how you find resultant vectors. So the last thing I'll do is I'll point out that with this, if you draw the vectors correctly, you can actually see it. And it works with as many vectors as you might have. So let's say that there I have vector A, and then I have vector B, and I have vector C, and I want to figure out the resultants of all of these. C usually goes down that way. And we'll put that at the origin. Well, the way to do it is to make sure you put all of the vectors tip to tail. There's that one tip to tail. And there's that one tip to tail. And if we then find the sum of them, that resultant vector, you'll see it'll always fulfill all of them from its origin to the end point if they're put tip to tail. And that's the same thing with our vector addition, is that formula of A, B, and we can even add C into it, being equal to their component parts added together. A of y, B of x, plus B of y, and C of x, plus C of y. When you add them all together downward, you're going to get a resultant components. that you can then figure out the resultant value and angle. Okay? So it works out no matter how you do it. Hope this helps.